Welcome to the first learning outcome, where we get to grips with measures of spread, the tools that tell us not just where a set of data sits, but how much it varies. It's the difference between knowing the average and really understanding your numbers. Whenever we've got a pile of numbers, statistics helps us boil them down so we can compare and decide. There are really two questions worth asking about any data set. Where is the center, and how spread out are the values? Think of two sales teams, both averaging 20 deals a month, one steady on 19, 20, 21, the other swinging between 5 and 35. Same average, completely different stories, and that's exactly why spread matters as much as the average. Let's start with the three ways of pinning down the center. The mean is the one everyone knows. Add all the values up and divide by how many there are, which we write as x bar equals the sum of x divided by n. The median is the middle value once you've put everything in order, and the mode is simply the value that crops up most often. Say 5 shops take 10, 12, 15 and £21,000. The mean is 14,000, the median is 12,000, and the mode is 12,000 as well because it appears twice. Now for spread, and again we've got three tools. The range is just the highest value minus the lowest. Quick, but one freak value throws it right off. The interquartile range looks at the middle 50% of the data, so it shrugs off outliers. And the standard deviation measures the typical distance of every value from the mean, which is why it's the workhorse of the three. We'll build up to that one carefully. Let's put those to work on some real figures. A shop records its daily sales of one product over a week: 8, 5, 9, 12, 5, 7, and 10 items. First, order them 5, 5, 7, 8, 9, 10, 12. The mean is all of those added, which comes to 56, divided by 7 days, giving 8 items. The median is the fourth value in the ordered list, which is also 8. The mode is 5, since it's the only value that appears twice, and the range is 12 minus 5, which is 7 items. When a data set gets large, listing every single value becomes unwieldy, so we bundle the numbers into class intervals, say 0 to 10, 10 to 20, and so on. It makes the data far easier to read, but there's a trade-off. We lose the exact individual figures. To work out an average, we treat every value in a class as if it sat at the midpoint, so for the 20 to 30 group, we'd use 25. Because of that, any average we get from grouped data is an estimate rather than an exact answer. Here's a real example: the time 40 customers spent browsing a website. The classes run in 10-minute bands from 0 up to 50 minutes, each with a midpoint of 5, 15, 25, 35, and 45 minutes. The frequencies tell us how many customers fell in each band: 4, then 9, then 13, then 10, then 4. Notice the 20 to 30-minute band is the busiest, with 13 customers. We'll use this exact table to estimate the mean next. To estimate the mean, we multiply each midpoint by its frequency to get a column of f times x values, then add them up. For our browsing data, that sum, the sum of fx, comes to 1010. The frequencies add up to 40, which is our total number of customers. So the estimated mean is the sum of fx divided by the sum of f. That's 1010 divided by 40, which works out at 25.25 minutes. Remember, it's an estimate because we leaned on those midpoints rather than the raw times. With grouped data, we can also spot the modal class and the median class. The modal class is simply the band with the highest frequency, and here, that's the 20 to 30-minute group with 13 customers. For the median, with 40 values, we're after the 20th and 21st. Building running totals: 4, then 13 by the top of the second band, then 26 by the top of the third, shows those middle values land inside the 20 to 30 band. So that's our median class 2. Standard deviation sounds intimidating, but the idea is simple. It measures the typical distance of the values from the mean. A small standard deviation means the data huddles tightly around the average, nice and consistent. A large one means the values are scattered far and wide. Unlike the range, it uses every single value, so one rogue number doesn't dominate. You'll find it everywhere, from quality control on a production line to measuring risk in finance. Let's walk through how it's actually calculated. Step 1. Find the mean, x bar. Step 2. Find each value's deviation from that mean. In other words, x minus x bar. Step 3. Square every deviation, since squaring conveniently kills off the minus signs. Step 4. Average those squared deviations, and that average is called the variance, the sum of the squared deviations divided by n. Step 5. Take the square root of the variance, and that brings us back to the original units. That's your standard deviation. Time for numbers. Take the 7 values 4, 6, 8, 10, 12, 14 and 16. They add to 70, so the mean x bar is 70 divided by 7, which is 10. Now find each deviation from 10, square it, and add them all up. That total comes to 112. The variance is 112 divided by 7, which is 16. And the standard deviation is the square root of 16, which is 4. So on average, these values sit 4 units away from the mean. And a neat check. The deviations themselves always sum to 0, which is exactly why we square them. Here's why this matters in the real world. Imagine 2 machines, both filling bags to an average of 500 grams. Machine A has a standard deviation of 3 grams. Machine B, a standard deviation of 11 grams. The average alone can't separate them. They're identical on that score. But Machine A's bags nearly all land within 3 grams of target, wonderfully consistent, whereas Machine B's swing by 11 grams, so far more bags come out under or overfilled. For quality control, you'd pick Machine A every time, and it's the spread, not the average, that made the decision. A couple of things to keep in mind when you read a standard deviation. Because it's in the same units as the data, grams, minutes, pounds, it's easy to interpret directly, but always judge it against the mean. A standard deviation of 5 is huge if the mean is 10, yet trivial if the mean is 1,000. That's where the coefficient of variation helps. Dividing the standard deviation by the mean lets you compare spread fairly across different data sets. Broadly, a bigger standard deviation signals more risk or inconsistency, a smaller one more stability. Cumulative frequency is just a running total of the frequencies as you climb through the classes. We plot that running total against the upper boundary of each class, and when we join the points with a smooth curve, we get what's called an ogive, or cumulative frequency curve. It's a genuinely useful shape, because from it, we can read off the median, the quartiles, and in fact, any percentile we fancy. Let's build one. Picture a dataset of 60 values grouped in tens. The frequencies 3, 8, 15, 16, 12, and 6 add up as running totals to 3, 11, 26, 42, 54, and finally 60. Because there are 60 values in total, the median sits at the 30th value, the lower quartile at the 15th, and the upper quartile at the 45th. Those 3 positions are what we'll go hunting for on the curve. Reading the median off the ogive is lovely and visual. With 60 values, the median is at a cumulative frequency of 30. That's n divided by 2. So you go to 30 on the vertical axis, Draw straight across to the curve, then drop down to the value axis. For this data that lands at about 33. The very same trick gives the quartiles. Go across at 15 for the lower quartile and at 45 for the upper. The curve has turned a table of totals into readable statistics. Let's define those quartiles properly. They chop the ordered data into 4 equal parts. The lower quartile, Q1, sits a quarter of the way up, at a cumulative frequency of n divided by 4. The median, Q2, is halfway, at n divided by 2. And the upper quartile, Q3, is 3/4 of the way, at 3n divided by 4. The interquartile range is simply Q3 minus Q1, the spread of the middle half of the data, and because it ignores the extreme quarter at each end, outliers can't distort it. Back to our 60-value dataset to find the interquartile range. The lower quartile is at a cumulative frequency of 15. Reading across and down gives Q1 of about 22. The upper quartile is at a cumulative frequency of 45, which reads off at about 44. So the interquartile range is Q3 minus Q1, that's 44 minus 22, which is 22. In plain terms, the middle half of our data spans about 22 units. A box plot is a brilliant way to picture spread because it shows the 5-number summary at a glance: minimum, lower quartile, median, upper quartile, and maximum. Take a set of delivery times summarized as 12, 24, 31, 38, and 58 minutes. The box stretches from 24 to 38, spanning the interquartile range with the median marked at 31 inside it. The whiskers reach out to 12 and 58, and that long right whisker up to 58 flags a few slow deliveries, dragging the maximum up. Box plots really come into their own when you're comparing 2 or more groups side by side. So which measure of spread should you reach for? The range is quick, but easily wrecked by one unusual value. The interquartile range shrugs off outliers, making it ideal for skewed data. The standard deviation uses every value and suits roughly symmetric data and any further analysis. Think of house prices, where a handful of mansions pull the mean and range right up. There, the median and interquartile range give a far fairer picture. The honest answer is, there's no single best measure. You match it to the data. Let's gather the threads. Central tendency, mean, median, and mode locates the center, while spread, the range, interquartile range, and standard deviation tells us how variable the data is. For grouped data, we lean on class midpoints, so the estimated mean and the modal and median classes are all estimates. Standard deviation is the typical distance from the mean. Square the deviations, average them for the variance, then take the square root. And the cumulative frequency, give hands us the median, the quartiles, and the interquartile range straight off the curve. That brings us to the end of measures of spread, and you should now be comfortable moving from an average to a full picture of how data varies. If you'd like to consolidate, the reading list points you towards friendly starting points like Rowntree's Statistics without tears, along with Crawshaw and Chambers for more worked practice. The Office for National Statistics site is well worth a browse for real distributions of things like UK earnings, and Corbett Maths has short videos if you want to see these calculations demonstrated again. Have a look, try a few examples by hand, and the ideas will really settle.